Welcome. My name is Chandima and I am glad you are here. Before we start the technical content, the systems, the APIs, the architecture, we are going to spend 2 hours on something that will matter more than any single concept you learn this week. We are going to talk about how to learn. This is day zero, not day one. That is intentional. Day zero comes before everything else because the habits you build today will decide how much you retain from day 1 through day 5 and how much you grow in the months and years that follow. So take a breath, open a notebook, and let us begin. Let me explain why this day exists. The 5-day crash course moves fast. Each day introduces a new layer of system design. There is no slow start. Day 1 covers requirements and system boundaries. Day 2 covers APIs, databases, and caches. Day 3 covers quality and reliability. By day 4, you are drawing full architecture diagrams and writing decision records. Without strong learning habits, interns who attend this week often hit a wall. They memorize definitions but never build mental models. They can repeat the words but cannot apply the concept. They watch sessions, passively nodding along, taking notes, and retaining almost nothing. A week later, they get stuck and wait, afraid to ask what feels like a dumb question, and so they fall further behind. And some use AI to generate answers they cannot understand, cannot defend in a review, and cannot build on when the next concept arrives. Day zero is a 2-hour investment. That is all. 2 hours today to build the habits that will make every other day click. That investment will pay dividends across this entire week and across your career. Let me show you the whole week so you know where you are headed. You are here at day zero, learning to learn. Everything you absorb today, the growth mindset, the active learning techniques, the note-taking system, the way to use AI wisely will apply to every single session that follows. Day 1 is systems thinking and requirements. You will learn to describe any software product in a way that an engineer, a manager, or a customer can instantly understand. You will learn the 5 words that form the vocabulary of system design. Day 2 is building blocks, APIs, databases, caches, queues, the Lego pieces of every modern application. You will learn not just what each one is, but when to reach for which. Day 3 is quality and reliability, speed, availability, security, and how to measure all of these with real numbers rather than vague adjectives. Day 4 is end-to-end system design. You will put everything together, architecture diagrams, architectural decision records, and a real design review with your peers. Day 5 is aspects as contracts. You will write a specification sharp enough to drive an AI coding agent. That is the skill you need before you join your first project team. 5 days. One foundation built today. Now let us talk about mindset. This is not soft or optional. There is real research behind this. A psychologist named Carol Dweck at Stanford University spent decades studying how people respond to difficulty and failure. She found that people tend to hold one of two beliefs about their own ability. The fixed mindset says, talent is fixed. You either have it or you do not. If you struggle, it is because you are not naturally good at this thing. Failure is a ceiling. It shows you your limit. Effort is pointless if you are not wired for it. You may have heard people say, or thought yourself, I am just not a tech person. That is the fixed mindset speaking. The growth mindset says, ability is built through effort, strategy, and time. Struggle does not mean you are failing. It means you are learning. Failure is data. It shows you exactly where to go back. The person you are in month 1 is not the person you will be in month 6. Dweck found that a single word changes how the brain responds to difficulty. That word is yet, not I cannot do this, but I cannot do this yet. The word yet moves failure from a permanent state to a temporary one. It opens a door. Every time this week you feel stuck, and you will feel stuck, that is guaranteed at the word yet. I do not understand this yet. I cannot see the pattern yet. That is your cue to lean in, not step back. There is a pattern that almost every engineer goes through when learning something new. I want to name it so that when you hit it this week, you recognize it instead of panicking. At the beginning, sometimes, for days or even weeks, concepts do not connect. Everything is new. You read something, you nod, and then 5 minutes later, you cannot explain what you just read. This is the confused stage. It is normal. It is not a warning sign, it is just where learning starts. Then something shifts. Patterns begin to appear. You start recognizing things you have seen before. Oh, this is similar to that thing from yesterday. Momentum builds. This is the clicking stage. You still make mistakes, but you can feel yourself improving. And eventually, you reach confident. You can explain what you know. More importantly, you know what you do not know yet. That awareness, knowing the shape of your own gaps, is actually what mastery beginning looks like. Here is the important thing: mastery is not talent, it is time on task plus reflection. The habits you build today, retrieval practice, atomic notes, asking good questions, they compress this curve. They move you from confused to clicking faster than passive learning ever can. One engineer told me something that stuck with me. He said, "Week 1 feels like drowning, week 4 feels like swimming. The water did not change, I did. Hold on to that." Let me show you the most important distinction in all of learning science: the difference between active and passive learning. Passive learning looks productive. You watch a video, you read through your notes again, you follow along as someone codes, and nod when it makes sense. It feels like learning. The retention is very low. Studies show that passive review produces roughly 20 to 30% retention after 1 week. Active learning is uncomfortable. You close your notes and try to reconstruct what you just learned. You explain a concept back in your own words, out loud, even if only to yourself. You draw the system from memory before checking if you got it right. You write code without looking at the example and then compare. It feels harder. The retention is 3 to 5 times higher. There is a simple rule: doing beats, reading beats, listening. Every session this week, after the slides end, close your notes, open a blank page or a blank whiteboard. Try to reconstruct what you just learned. What were the key ideas? What were the examples? What was the diagram? The struggle to recall is where the learning actually happens. That feeling of difficulty is not a sign that you do not understand. It is a sign that your brain is working. Welcome it. Active learning has two powerful tools built on the same idea: retrieval practice and spaced repetition. Retrieval practice means forcing your brain to recall information rather than reread it. After this session, instead of going back through the slides, close everything and open a blank page. Write down everything you remember. Do not check your notes yet. Just write. The act of struggling to pull information back out of your memory strengthens that memory far more than reading the slides a second time would. Spaced repetition takes this further. You review material at increasing intervals: tonight, then day 3, then a week later, then 3 weeks after that. Each time you successfully recall something, the next review can be further in the future because the memory is stronger. Tools like Anki and Obsidian flashcards are built for this, but even a simple review later tag in your notes will work. This is exactly why the Day Zero challenge includes a day log. At the end of each day, you write 3 things you learned without looking at any slides. And on day 5, you return to your day 1 notes and ask, what still holds? What changed? That is, spaced retrieval built into the structure of the week. The research on this is very clear. Testing yourself is more effective than restudying. Always retrieve before you reread. Richard Feynman was a Nobel Prize-winning physicist who was famous for being able to explain complicated ideas in simple language. He had a method for learning that is now named after him, and it is the single best test I know for whether you actually understand something. The Feynman technique has 4 steps. Step 1. Choose a concept you think you understand. It can be anything: an API, a cache, a for loop, a database index. Step 2. Explain it simply. Write out or say out loud an explanation using plain language. No jargon. Imagine you are explaining to a 14-year-old who is curious but has never studied this subject. Step 3. Find the gaps. Wherever your explanation breaks down, gets vague, or uses a word you cannot define in turn, that is a gap. That is a place where you have a label but not actual understanding. Step 4. Go back and fill the gap. Return to the source material specifically for that gap, not for a general reread only for the specific thing that broke. Then re-explain until the simple version holds all the way through. The test is this: if you cannot explain a concept without using the concept name, you do not yet understand it. An API is an application programming interface, is not an explanation. It is just the words rearranged. An API is a set of rules two programs agree to follow so they can share information, like a waiter who takes your order to the kitchen and brings the food back. That is an explanation. Now we are going to try this right now. This is a 10-minute pair activity. Here is what you will do. Pick one concept you already know or think you know, something from your college coursework or your own reading. It could be an API, a database, a loop, a function, a server, a cache, a login flow, or what a bug actually is. Write a single sentence explaining that concept using zero technical jargon. None. If the concept name is in your explanation, rewrite it. Then your pair reads it and gives feedback. Does this make sense to someone who has never heard the term? Here is the example. If I ask you to explain what an API is, and you write, an API is an application programming interface, that is the wrong kind of explanation. You have used the term to define itself. Someone who did not know what an API was before reading that sentence still does not know. The right kind looks like this. An API is a set of rules two programs follow to request and share information, like a waiter taking your order to the kitchen and bringing food back. Now the concept is grounded in something the reader can picture. They understand the function, the role the API plays before they ever learn the name. Do this for your concept. Find where your explanation breaks. That break is where your real learning starts. Most engineers are never taught how to read documentation. They either skip it entirely and search Stack Overflow, or they try to read it front to back like a novel and feel overwhelmed by the third page. There is a better way. Step 1. Scan the structure. Read only headings and subheadings. Do not read any body text yet. Build a mental map of what exists and where it lives. You need to know the shape of the documentation before you can use it effectively. Step 2. Find the quick start. Go directly to the Getting Started or Quick Start section. Examples show you how the tool is meant to be used. They reveal the intended design. Definitions without examples are hard to anchor in memory. Examples give the definition somewhere to attach. Step 3. Build the happy path. Trace the normal case end to end before you touch edge cases, error handling, or configuration. Build a complete mental model of the thing working correctly. Once you have that, everything else becomes a variation on a theme. Step 4. Then the reference. Return to the full reference section only when you need a specific detail. Looking up one specific thing in context is far more efficient than reading the full reference before you have built any mental model. The anti-pattern to avoid: reading documentation front to back like a novel. Docs are reference material. They are not designed to be read in order. Use them the way you use a map: orient first, then navigate to where you need to go. Let me make the example first approach concrete with something many of you will encounter on day 5 and in your first weeks on a team. Imagine you are learning about promises in JavaScript for the first time. The definition first approach gives you something like this. A promise represents the eventual completion or failure of an asynchronous operation and its resulting value. A promise is in one of these states: pending, fulfill, rejected. You read 200 words and still cannot write a single line of code that uses one. The example first approach gives you this. Start with a real snippet. Fetch/API/users dot then function where R comes in, r.json dot then function where data comes in, console.log of data. You run it. You see the list of users appear. Now you know three things from watching it work. Fetch returns a promise, dot then handles the result when it arrives, and you chain them. Now you read the definition and it snaps into place because it is a label for something you have already seen in action. The definition becomes useful the moment it has something to attach to. The rule: find an example first, run it, understand what happens, then read the definition to confirm your mental model, not the other way around. This is one of the highest value skills you will build this week. Not coding, not design, asking good questions. Most people ask incomplete questions. It is not working. I do not understand this. My code has an error. How does this work? These questions put the entire burden on the person answering. They cannot help you without first asking 5 clarifying questions to understand what you actually tried, what you expected, and what went wrong. You have wasted their time and yours. A good question has 3 parts. Context: what are you trying to do? What is the goal? What environment are you working in? Tried: what have you already attempted? What was your reasoning? What did you expect to happen? Stuck: where exactly did things go wrong? What error did you see? What exact output or behavior? A question that fills all 3 parts looks like this. I'm trying to fetch user data from /API/users. I used fetch and expected a list of user objects, but I got undefined. The console shows no error. Here is my code. Now, a senior engineer can help you in one response. They know what you tried, what you expected, and what broke. They do not have to interrogate you. One more thing. Seniors at BISTEC value a well-formed question as much as they value the answer. It shows you can think clearly about a problem, which is a more transferable skill than knowing any one specific fact. Let me make the 3-part format even more concrete so you can use it immediately. Context C. What are you building? What should it do? What environment are you in? This is the setup. It gives the reader enough background to understand why you are doing what you are doing. Try T. What did you attempt? What was your reasoning? What result did you expect? This shows that you made an effort, and it tells the reader what you already know and what you were thinking. Most importantly, it often contains the clue to the answer. Stuck is: what actually happened? What exact error message or output did you see? Where precisely does it break? The more specific this is, the faster someone can help you. Here is a real example. Context: I am building a login form in React. Tried: I called setUser with the data from the API inside a use effect and expected the user to stay in state across renders. Stuck: but the value resets on every re-render and I am getting a stale closure warning in the console. From that one message, a senior engineer immediately knows what component you are in, what you tried, what you expected, and what the symptom is. They can probably give you the answer in 3 sentences. Practice writing CTS every time you get stuck this week. Not just when asking a person, write it for yourself. Half the time, writing it clearly will show you the answer before you send it. There is a famous technique in software engineering that sounds silly and works almost every time. It is called rubber duck debugging. Here is the method. Explain your problem out loud, line by line, to an imaginary listener. It could be a rubber duck on your desk, it could be a house plant, it could be thin air. It does not matter. The listener does not need to understand, they just need to exist as a target for your explanation. The act of forming a coherent explanation forces your brain to slow down. You have to fill in the gaps in your own understanding. You surface assumptions you did not know you were making. You cannot skip steps the way you do when reasoning in your head. And most bugs, most debugging sessions end before you finish the explanation because you say something and then hear yourself say it and realize that is not right. Here is how to do it. State your goal out loud. I want this function to return the sum of all the numbers in this list. Then walk through your code line by line. This line does X, so Y should happen. This line does Z. When you say something that does not match what you actually see happening, that is the bug. Use rubber duck debugging before you ask for help. If you cannot explain the problem clearly and coherently to the duck, you are not yet ready to ask a human. And they will ask you exactly the same clarifying questions the duck would have if ducks could speak. Your brain is not storage, it is a processor. Notes free your brain to think rather than spending energy trying to hold everything in working memory. There are 4 reasons notes matter in a career in engineering. First, you will encounter the same problems again. A searchable note is faster than memory, and memory degrades over time. The solution you figured out 6 months ago lives in your note, not in your head. Second, writing a note forces clarity. Vague ideas that survive in your head often collapse the moment you try to write them down. If you cannot write it clearly, you do not yet understand it clearly. The note is the test. Third, notes build a personal knowledge base over a career. It is compound interest. Every note you write this week is a small investment. In 5 years, the collection is a substantial asset. For tools, you have several good options. Obsidian is local markdown, offline first, with powerful bidirectional links. It is the best option for long-term knowledge management if you are willing to invest a little time in setup. Notion is collaborative, web-based, and has a useful free tier good if you are working with a team. Google Docs requires zero setup and is searchable from day one, a fine starting point. And for engineers, a markdown file in your project folder inside VS Code is engineering native and requires no new tool at all. The best node system is the one you actually open. Choose one tool, use it this week, commit. There is a right way and a wrong way to take notes. The difference is not the tool, it is the structure. The wrong way is what I call the dump note. One giant file called Day 2 Notes, with everything from the day mixed together. Lecture notes, code snippets, things you want to look up later, questions you thought of, all in a pile. You cannot find a specific concept without reading the entire file. Ideas from different sessions sit in different files and never connect. 3 months later, it is effectively useless. The right way is the atomic note. One note per idea, not one note per session, one note per concept. What is a cache is one note. Why use a database index is a separate note. HTTP versus HTTPS is another separate note. Each note has 4 things: the concept name, a plain definition in your own words, a concrete example, and a when to use or not use section. And here is the powerful part. Nodes link to each other. Your cache node links to your database node, which links to your index node. A year from now, each individual node is still independently useful, and when you follow the links, you rebuild the mental model of the whole system. The insight is this: linking nodes creates understanding, not just storage. A network of small connected nodes builds a mental model. A pile of large disconnected nodes just adds to the pile. You are going to spend most of your career working alongside AI tools. On day 5, you will use AI to help write specifications. In the months that follow, you will use AI coding assistants to generate code. This is the reality of modern software engineering. But there is a right loop and a wrong loop. The wrong loop: see problem, paste into AI, copy output, submit. You get the answer. You do not understand why. You cannot explain it. When the next problem is slightly different, you are stuck again and again. In 6 months, you have the same gaps you started with because the AI did the thinking, not you. The right loop has 4 steps. First, attempt. Try the problem yourself first. Even if your attempt is wrong, it trains your brain. It forces you to engage with the problem actively. Second, ask AI to check. Share your attempt. Ask, is this right? What did I miss? Not, write this for me. Third, verify against docs. AI is often correct, but it makes mistakes. Cross-check anything important against an official source. Fourth, restate in your words. Write a note using the Feynman format. The concept now belongs to you. The shortcut that costs you. Copying an AI answer without attempting the problem means you trained AI to think, not yourself. Let me make the difference between good and bad AI use very concrete, because you will face this choice dozens of times this week and hundreds of times in your career. Good AI use sounds like this: I wrote this solution. Does it look correct? What would you improve? The attempt is yours. The AI reviews it. Good. Explain why this approach is better than what I had. Now you are building understanding. Good. I am getting this error message. What might cause it? I will try to fix it myself first. You are using AI to point you in a direction, not to do your job. Good. Generate 3 variations so I can compare the trade-offs. You are using AI to expose options, and you are the one evaluating them. Good. Bad AI use sound like this. Write the solution for this challenge. Here's the question. Give me the answer. Copying AI output without reading it. Submitting code you cannot explain line by line. The question is not, can I get AI to produce this? You can always get AI to produce almost anything. The question is, can I explain and defend what I submitted? Because in a code review, in a design review, in a conversation with a senior engineer, you will be asked, and if the answer is the AI wrote it and I do not know why, you have not learned anything and you have not delivered anything of value. AI that does your homework trains your fingers, not your brain. Now, it is time to put the first tool into practice. Your Day Zero challenge is to build your personal learning system today during this session, and then use it for the rest of the week. Here is what you need to create. Open your note-taking tool of choice: Obsidian, Notion, Google Docs, or a Markdown file in VS Code. Create your first note. Section 1. What I already know. Write 3 to 5 bullet points about things you believe you already understand in software engineering. Be specific. Not I know programming. Something like, I know what a for loop does, but I am not sure how it differs from recursion in memory usage. Specificity is the point. Section 2. What I want to understand by day 5. 3 concrete testable learning goals. A bad goal is understand AP is. A good goal is I can explain what HTTP status 401 and 403 mean and when each is returned without looking it up. Section 3 My Learning Style. 3. Honest questions about yourself. Do I learn better by reading, watching, or doing? When I get stuck, what is my first instinct? What is one learning habit I want to build this week? Section 4 The Day Log. Leave this blank. You will add 3 to 5 lines every evening for each day this week. That is your learning plan. The full rubric is in challenge.md. 10 points. 8 or above means strong learning discipline. Day 0 is complete. In the last 2 hours, you have built something more valuable than any fact from days 1 through 5. You have a framework for learning. You know the difference between passive and active. You can apply the Feynman technique the moment something feels unclear. You know how to ask a question that a senior engineer can actually answer. You have a note-taking system set up and ready, and you know the right loop for using AI as a learning partner. Every one of those tools applies starting tomorrow morning. Here is your homework for tonight. It takes 15 minutes. Set up your learning journal if you have not already all 4 sections. Write the first entry in your day log for day 0. Pick one concept from today growth mindset, retrieval practice, atomic notes, any of them, and do a Feynman check. Explain it in one paragraph with no jargon and at least one analogy. Tomorrow is day 1, system thinking and requirements. We start with what a system actually is, and we use a real Sri Lankan product you already know, Pick Me, as our first example. Get a good night's sleep, come with your notebook, your week starts now.